Now we look at adapting another concept that you know from set theory or methods of proof or some other basic course that you've taken, and that is the notion of the range of a function. So the range of a general function f from a set x to a set y is denoted ran f. And so this is all the elements in the codomain such that they look like f of something. So it's like saying there's some x that maps to it. And so it's worth noting here that based on the definition, since we're in Y now, we see that the range of f is a subset of the codomain of f, just like the null space was a subset of the domain. And so this is sometimes thought of as the set of all outputs. And so we can write this in the form of an indexed set by saying that this is everything with the form f of x, where x ranges through the where x ranges through the domain of f. So it's all possible outputs for any of the given inputs. And then so it's sometimes even denoted for short as f of the big set x. And in this context, it's also sometimes called the image of f, or the image of x under f. Okay. So now we have a corresponding term to think about, which is surjectivity. So a function from x to y is surjective if and only if the range of f is equal to the entire codomain. So, said differently, this means for every element of the codomain, there exists an x in the domain with f of x equal to y. So it's basically saying that the equation fx equals y can always be solved. And when I say can always, I mean for any choice of y. Okay. So now we're going to look at the special case when our function is a linear map. And in previous clips, we saw that there's a neat trick to see when the function is injective. We don't have, and that's characterized in terms of the null space. We unfortunately don't have a nice slick way to do something comparable in this case, but we do at least have that the range is a subspace of W. And so since 0 is in V and T is linear, we always have that T of 0 is in the range. And so then the question is, what else do you have in the range? And so proposition 319 says that you get a whole subspace in the range. So for a given linear map, The range is a subspace of the codomain. Okay, and so again for the proof, by proposition 1.34, we just need to check the closure properties at this point. So suppose we have W1 and W2, both elements of capital W. Okay. Oh, sorry, what am I doing? I wrote the wrong thing. Both elements of range of T, because we want to show range of T is a subspace. Okay, so then there are, since W1 is in the range, then there's a V1 that maps to it. And there's also some V2 that maps to W2. All right. Now, if we look at the sum of these two, W1 plus W2, is this in the range of T? Well, I can use what I wrote down on the previous step. So I've got W1 is TV1, and W2 is TV2. And then what do you have to do? Well, let's see. We're trying to manipulate this expression somehow. And we're trying to show that W1 plus W2 is in the range of T. So this expression that I just wrote down here, this sum, I want to make that look like T of something. And after staring about it for some minutes, you notice, oh, you know what? I can use linearity to pull out the T. And now I've got W1 plus W2 expressed as T of a thing. There's the thing is V1 plus V2. So I win. Okay. And if I let lambda be a scalar, then let's see, I need to check lambda times W1, right? And I want that again to be back in the range. So to be in the range, this needs to look like T times something. Okay, let's see. So lambda W1 is what? Well, all we know about W1 is that it can be written as T of V1 for some V1, right? And so then I can do the same thing, and I can pull the lambda inside. And so now I have my guy expressed as T of something from the domain. That means that my guy is in the range. And so I'm done.